Hello everyone, welcome back to the channel. Today we are entering one of the most beautiful bridges in all of quantum mechanics, the bridge between probability and expectation values. This idea is so central that Griffiths introduced it in chapter 1 itself. But here's the good news, it's actually built on mathematics you already know from high school statistics. So let's start from everyday life and gradually walk into the quantum mechanics. So we want to understand the probability and its connection with the expectation value. So imagine you walk into a room with exactly 14 people. Everyone has different age distribution. So suppose we are having one person at age 14, one person at age 15, 3 persons at age 16, 2 people at age 22, followed by 2 people at age 24 and 5 people at age 25. So we are having total 14 people, right? And if I want to carry out the probability of the person at age 15, if I select the random person, then that would be P of 15 equals to 1 of 11. So that's it. Probability is the fraction of outcome. Now this idea extends to every age group. So suppose I want to find P of 14, it would be 1 by 14. P of 16, it would be 1 by 14. P of 25, it would be 5 by 14. So this is what Griffiths called discrete probability, right? But here's the twist. When we ask questions like what is the average age, okay, what is the average age? We don't just average the list, we average with probability weights. The mean age using classical probability is average of j, which is equal to sigma of j n of j divided by 40. And that is equals to sigma of j from j is 0 to infinite, j into p of j. So plugging these numbers, we can consider the all people's age using this equation and obtain the mean age. That would be 14 into 1 by 14, 15 into 1 by 14, 16 into 3 by 14, 22 into 2 by 14, 24 into 2 by 14, 25 into 5 by 14. So we get the age of 21, right? So this quantity does not have to be equal to any actual person's age. Maybe nobody is 21 years old from this group, but the average can still be 21. This is the first deep message Griffiths gave us, that the expected value is not literally the value you expect to get in a single measurement. This is where the phrase expectation value misleads students in statistics and of course in quantum mechanics. It simply means the average over very many trials. So the more we try to make the measurements, we would like to get the results as we want. And those results should lie in that range. And that range is composed of expectation values. To understand how spread out the ages are, we should compute the variance and standard deviation. These are most generalized concepts in the statistics. So variance is defined as the sigma square, and that is the average of delta j square, right? And that is given by the j square minus average of j square minus j average of j and that square, right? So what I'm trying to tell you that of course we are having the derivation here, right? We can get simply the formulation with the help of this little derivation. We can get sigma is equal to under root of this term, which is average of j square minus the square of average of j. So these were discrete variables. We want to get expectation values for continuous variables. Why does Griffiths include this? Because later in quantum mechanics, this becomes the backbone of uncertainty principle, wave packet spread, measurement precision. So this first chapter builds the statistical foundation for quantum ideas. Now the million rupee questions, how does this link to quantum mechanics? In quantum mechanics, you never get a definite result until you measure. Every possible outcome has probability, and the wave function psi of x contains all the probability information. So instead of asking what is the probability that person's age is 25, you may ask what is the probability of finding the particle at position x? And the answer is p of x dx, that is known as psi of x square dx. This is identical to saying p of j in the discrete case. The Born rule, which we have seen so far, that psi of x square mod of psi of x square is equal to probability density. This is the statistical foundation of quantum mechanics. In real life, age is discrete, but position is continuous. So probability becomes probability density, that is rho of x, that is equals to psi of x square, which we have seen so far in the previous videos. So probability between A and B, that is P of A less than X less than B, that is given by integration from A to B, rho of X dx. Total probability is 1. So if I take the range from minus infinite to plus infinite, this rho of X is known as the probability density, as we have mentioned here, and that is mod of psi of x square. This is exactly the continuous analogous of sigma j p of j equals to 1, which we have seen above. Now comes the big moment, the link between probability and expectation values. In classical probability, f of j is equal to sigma f of j p of j, as we have mentioned earlier. But in quantum mechanics, that f of x is equal to the integration from minus infinite to plus infinite into f of x into psi of x squared dx. And of course, that rho of x is psi of x squared, and which is probability density. Yes, so this is why Griffiths start chapter 1 with simple age statistics, because the rule is identical. So the expectation value of position is given by x, average of x equals to minus infinite to plus infinite integration x into rho of x dx. The expectation value of kinetic energy can also be written in terms of operator form. Momentum is also can be written in terms of operator form. So we'll see it later. In other words, operators replace classical variables. But expectation is always sum or integral of value into probability. So let's bridge everything in one sentence. Quantum mechanics is a theory where the wave function assigns probabilities to all possible outcomes. And expectation values are just the statistical averages of those outcomes, calculated using the wave functions. So probability comes from psi square. Expectation comes from average over many measurements. Spread and variance comes from the source of uncertainty principle. Operators, that is mathematical tools to extract averages. This is why Griffiths started the book not with the Schrödinger equation, not with operators, but with probability. Because quantum mechanics is fundamentally statistical. And here, if you understand classical probability, averages, variance, distributions, you already understand 70% of mathematics behind quantum expectation values. Quantum mechanics simply wraps this these familiar ideas inside a wave function. So if you enjoyed this video and want more beginner-friendly Griffiths-based tutorials, hit like, share this with your friends, of course physics friends, and subscribe for next episodes. Next time, we'll explore operators, eigenvalues, and measurements, the real machinery behind quantum predictions. Thanks for watching, and as always, stay curious.